Okay, we're going to wrap up Standard 13 this week, looking at calculating conditional probabilities by sketching what are called tree diagrams. I can outline two different conditional events using tree diagrams and calculate some interesting probabilities using that diagram. I think we'll kind of look at this today and tomorrow, and maybe come back and review and quiz next week over Standard 12 and 13, kind of a big probability assessment. Looking at addition rule, multiplication rule practice from Standard 12, and conditional probabilities here in Standard 13. So let's read through this outline, talking about being injured while wearing a seatbelt. A recent DOT survey found that in 77% of all accidents, the driver was wearing a seatbelt. You either were or you weren't. 77% of drivers in accidents were wearing a seatbelt. Accident reports show that 92% of those drivers escaped serious injury requiring hospitalization. 92% of drivers that were wearing a seatbelt came away fine, escaped serious injury. But only 63% of the non-seatbelted drivers were fortunate enough to escape without serious injury. Let's outline this using a tree diagram. What two events are described in that scenario? If you wear a seatbelt, and then based off of wearing a seatbelt or not, what else would we know about? What other event? Whether you were injured or not, right? Serious injury. So let's start piecing this out. The first event, wearing a seatbelt or not wearing a seatbelt. That's what has to happen first. We know you either wear a belt or you don't. Let's start there. Think about what has to happen first as you're making your tree diagram. You wear a seatbelt and then you're going to get in an accident. So I have to start with the wearing the seatbelt event. What percent of drivers were wearing seatbelts?
77%.
What percent of drivers were not wearing seatbelts? It doesn't say it, but what would it be?
23.
Now, what happens after? What is the next event? You could be injured or not injured while wearing a belt. You could be injured or not injured if you're not wearing a belt. So from each of these two nodes in the tree diagram, we're going to draw two more branches, representing whether you're injured or not injured from wearing a belt or not. Does that make sense? Mm-hmm. We're going to split it up into four possibilities. Belt and injured, belt and not injured. No belt and injured, no belt and not injured. So not injured. All right, let's start with injured here. Not injured. Come down below. Injured. Not injured. Let's look at this second sentence to start filling in some more values for our tree diagram. Accident reports show that 92% of those drivers that were wearing a belt escaped serious injury. So where am I going to put that 92%? First place, second place, third place, or fourth place? Second. They were wearing a belt, and then they escaped serious injury, right? So wouldn't that kind of go right here? Yeah. Only 63% of the non-belted drivers were fortunate enough to walk away from the crash. Where's that 63% going to go? The very bottom. Want the other two places? Top should be 8% because it would just be the other part from the 92. If 92% of belted drivers were not injured, wouldn't the other 8% be belted drivers that were also injured? Yeah. 63% for the fourth place The one above it should be the other 37. All right, we've got all of the probabilities from the description put on the tree diagram. Now let's start multiplying. What's the probability that you were belted and injured? Well, I'm going to take 77% times 8%. I want this and this to happen. So I take 77% times 8%. What's the probability, or what proportion of all these drivers fell into these four respective categories? 0.77 times 0.08 is 6.16%. Let's come down and get belted and not injured. So that's 77% times the other 92%. 0.77 times 0.92. 0.7084. Not belted and injured. That's the 23% times 37%, or 8.51%. I'm just trying to find what part fell into each of these categories. So I'm multiplying across the tree diagram. Last one should be not belt and not injured. No belt and not injured. 0.23 times 0.63 is 0.1449. If I do this right, what should all four of these underlying values have to add up to? 100%, right? So if you're curious about whether you separated the tree out correctly, add up all of these final four values and it should make 100%. Okay, let's answer some probabilities here to the right. What is the chance someone will have an accident with a serious injury? If you have an accident with a serious injury, couldn't you either be wearing a belt or not wearing a belt? So which two probabilities do I have to add up together? These two here. You're injured while wearing a belt. You're seriously injured while not wearing a belt. So it's the sum of these two outcomes from the tree diagram. 6.16% plus 8.51%. I get 1467. There's about a 14 or 15% chance that you're going to have a serious injury if you get into a car accident, whether wearing a belt or not. Now we have some conditional probabilities to outline on parts B, C, and D. What are we assuming to start with for the question here on part B? Given someone was seriously injured, what's the chance they wear a seatbelt? What do we know to be true first?
They were seriously injured.
Okay, so what's the probability that you were injured if you were injured? What else has to happen?
You were wearing your seatbelt.
No belt. So this is going to be out of the probability of being injured. What part of that was also wearing a belt? Of all those that were seriously injured, what part was also wearing a belt? We're trying to answer in this question. Well, didn't we just answer the proportion of those that were injured in part A in the previous question?
Yeah.
So that's going to go on bottom. 0.1467. That's the part that had the serious injury. And of that part, how many were wearing a belt? Which of these four numbers from the tree diagram does that tell us? Belt and injured, that should be the 6%. Basically, I'm taking 6.16% divided by 6.16% plus 8.51%. Let's see, what is that? 4199. You were in a car accident and seriously injured, there's about a 42% chance that you were wearing a belt. I think C is the exact opposite. Of those seriously injured, what's the chance that they did not wear the seatbelt? So same setup. Of those seriously injured, what part was not wearing a belt? So we'll take the entire proportion of those that were injured, and of that proportion, what part was not wearing the belt? So of the same 0.1467% that was seriously injured from part A, which of these numbers was injured without the belt? 0.0851. So now I'm taking 0.0851 divided by the sum of 0.0616 plus 0.0851. I think this is just the exact opposite, so it should be the other 52% approximately. $58.01. If you were injured in an accident, there's a 58% chance that you were not wearing a belt. Let's finish this up with one more on part D. If you are not seriously injured, what is the chance that you were wearing a seatbelt? If you were not seriously injured, what is the chance that you were wearing your seatbelt? What are we starting with? What's been given for us to assume for our condition? Not injured. So we're talking about out of a different proportion. You were not injured. Of those that were not injured, what's the chance that you were now wearing the belt? What part were not injured? Where can I find the proportions for those that were not injured? I think there's a couple different ones. Isn't it the bottom two in each of these two branches? So I need to add those together. 0.7084 plus 0.1449. And of those two parts, which percent tells me those that were wearing the belt? Top one, 7084. Alright, so let's see here. Let's take 0.7084 divided by the sum of 0.7084 plus 0.1449. 83.02. You got in an accident and were not injured, there's an 83% chance that you were wearing your belt correctly. Are wearing a seatbelt and being injured independent events? Maybe we could use conditional probabilities to test to see if that's true. Are wearing a seatbelt and being injured in an accident independent events? Well, let's use conditional probabilities since that's what we're talking about. Let's compare a couple different probabilities. What is the probability you were wearing a belt? Should be given to us. Chance that you're wearing a belt is what? All right. Now, given that you were seriously injured, does that have any impact on the chance you were wearing a belt? Let's see if being seriously injured increases or decreases the chance that you were wearing a belt. Do I have that given probability already? Belt given injury, where is that over here? Belt given injury, I think I've already answered that. Where's it at? Right here, right? That was 0.4199. If you were wearing a belt, there's a 77% chance of that happening. Now, if I know you're seriously injured, the chance you were wearing a belt is now what? So what is being seriously injured due to the likelihood of you wearing a belt? Decreases it. Are these independent events at all? No, because these two probabilities were not the same. Being seriously injured in an accident lowers the likelihood of wearing your seatbelt. They were not the same, which should make sense. Don't save lives. All right, let's go ahead and get started on some practice.